Okay, so last class we were talking about specific heat capacity. That wrapped up that topic for us. We're moving on today to a new topic. We're going to be talking about mirrors, and we're going to start with plane mirrors. All right, so these are our objectives for today. We're going to describe how images are formed by plane mirrors, list the characteristics of images formed by plane mirrors, calculate image and object distance for a plane mirror, and explain how a periscope works. All right, so question, how do we see objects? What do we need to see? What happens? We can talk or type.
We see them with our eyes.
Yes, definitely. We need our eyes to receive what? What do our eyes need in order to interpret or make out an image?
Light.
Right, that's the word I'm looking for. Good. Okay. So when we see something, light bounces off of an object and enters our eye. Okay. That bouncing off is called reflection. And when that happens, we get an image that's processed by our eye. Interestingly enough, the image that we actually get is upside down. And then our brain has to interpret it, turn it right side up for us. And so we see the final image. Okay? That's how it works when we're looking directly at an object. But what about when the object is you? When you are the object, how do we see ourselves? What do we need in order to see ourselves?
A mirror.
Yes, definitely. We need a mirror. So we need something to kind of redirect the light rays into our eyes and produce an image for us. So in order to see our own reflections, the light must bounce off of a reflective surface. And typically, that's a plane mirror. So our everyday mirror that we use in our homes, in our bathroom, medicine cabinet, that's called a plane mirror. And it's not plain, as plain doesn't mean like just simple. Plane means flat, okay? So it's describing the shape of the surface. It's flat. So when light bounces off a smooth object, some of the light rays go off in random directions. As you can see, they're not all reaching the eye, but those that do reach the eye, they're the ones that would have bounced off of the mirror and we're able to receive them into our eyes. And for any given object, there are an infinite number of rays that bounce off of an object and enter our eye in order to make up the picture that we're going to see. Okay? So in this example, we're only showing a few of those rays just for simplicity. But if you look, what's happening is we see an image that looks like it's coming from behind the mirror. If we were to extend the rays, the reflected rays, so these, let me draw them for you. Okay, here we go. If we draw them in, and just point So these are our incident rays, we call them, the ones that actually strike the mirror, and then when they bounce back, these are our reflected rays. Okay? Now, the image that is produced, it's actually the spot where if we were to extend these rays back, this is where all the rays would meet up, as if it were coming from this spot right here. So when we talk about an image, we're actually talking about the point where all the light rays would meet up, okay? And if they meet up behind the mirror, then we call the image a virtual image. If they meet up in front of the mirror, then it would be a real image, okay? So let's look a little closer at this. So when we talk about reflection, we need to keep in mind that all of those rays, even though there are a lot of them bouncing off of that one object to produce a mirror. Morning, Kurtrinique. We're talking about plane mirrors. Even though, and I'm recording, so you can get the recording tomorrow to see what you missed. The rays that bounce off or reflect from the mirror, they follow the law of reflection. Anybody knows what the law of reflection states? Can we remember? Or do you need me to help you out? It's a little bit early. All right, I'm going to help you out. So the law of reflection states that the angle of incidence, those are the incoming rays, the angle that they make with the normal, which is a line that's perpendicular to the surface. So this line here would represent the normal. The angle that the incident ray makes with the normal is equal to the angle that the reflected ray, that's the one that bounces off of the surface, makes with the normal. Okay? So with that said, do you think you can answer this question for me? What is the angle of reflection? Is it A, B, C, or D?
A.
Okay, I'm hearing one answer. Someone said A. What are the rest of you thinking? It's okay if y'all still sleepy. I'm still waking up too. I'll get some coffee and wake up right now. All right, so A is a common answer. So the reason you're thinking A is a common mistake that a lot of students make. So you're looking at this angle here. But it's important to remember that the angle of incidence is between the normal and the incident ray. This is the angle of incidence. Okay? And the angle of reflection is between the normal and the reflected ray. Okay? So this one that goes in is the incident ray, and this one that comes out is the reflected ray.
What the answer will be?
So, very good. With that said, if we want to find this angle, we can clearly see that if the normal is perpendicular to the surface, then that means the angle between the normal and the surface is 90 degrees. And if we know this angle, then this one must be 90 minus 25, which is going to give us 65 degrees. So the answer is B. Okay? So good job. Who was that? That'd be Carisha.
No, that was me, Ariana.
Oh, good job, Ariana. All right. So you're going to see questions like that quite often. All right. So let's get back to talking about the virtual image. So if you have covered the topic extrapolation in math, where you have a graph and you can see the pattern of the graph, but it's not complete, and you want some data about the part of the graph that's not complete, well, what do? We simply follow the trend. We know that, okay, the graph is a straight line, so if I extend the line, I'm predicting that all the values behind that point will also follow the same trend, will be along that line. So we do the same thing, a similar thing for finding a virtual image. So when we look in the mirror, and let's say I look at, you're looking at my cup right now. Even if I put this cup behind my head, when I look in the mirror, it looks as if the image or the picture I'm looking at is coming from the mirror, not coming from behind me. Okay? So it's just a matter of perspective. And because of that, we interpret the image as coming from behind the mirror, and we find that the image is actually formed the exact same distance behind the mirror as the object is in front of the mirror. Okay? So if we extend the reflected rays behind the mirror, an identical image of the object seems to be coming from behind the mirror, as if all the light rays were reflected off another identical object that's at the same distance behind the mirror. So if I was looking directly at an object identical to this one, and it was in this exact same place, these broken lines would represent the path that the light rays would take when they bounce off of that object and enter my eye. Okay? So it's like we have two alternate paths. So this one is the virtual path. This is the path it would take if it was at this distance, but we just perceive it to be there. But the rays actually don't go past the mirror. Okay? I know it's a little bit confusing, but stay with me. All right, so the image that's formed behind the mirror is called a virtual image. And all that means is that it can be formed on a screen, okay? So when we use the projector in class and I shine the light at the whiteboard, that's a real image. You can see that on a screen. The light is hitting a surface and the image is made on that surface. That doesn't happen with a virtual image. Okay? All right. So some other properties of plane mirrors, besides the fact that they produce virtual images, are that the distance from the mirror to the object is the same as the distance from the image to the mirror. So object distance in front of the mirror is equal to image distance behind the mirror. That's a very important property. So it would serve you well to remember that. Also, when you look in a plane mirror, you notice that the top of your head matches the top of your head in the mirror. So your image is upright, you're not upside down. And you're also the same size. So the image that is formed on a plane mirror is going to be the same size as the object. All right, let's see if you can answer a couple of questions based on those properties. So we have a toy rabbit. This is our object here in front of the mirror. Which one of these shows the reflection of that
A.
object in a plane mirror?
A.
Correct. Okay, it's definitely A. Okay, we can rule out C and D right off the bat because they're what? Where are they located?
In front of the mirror.
Exactly. So that's not where the image of a plane mirror would be formed. Always behind the mirror for plane mirrors. So D and C were definitely out. And E, remember all of the light rays, they line up exactly with the object. Okay, so if we did this, then this would mean that the angles of reflection and incidence are not equal. So that would not be right either. It has to also be along the same line of sight. Okay, so B is no brainer as well. So next one. What about this one? So take a minute and read it. The diagram shows the arrangement used by an optician to test the patient's eyes using a chart and a mirror. The chart is placed behind the patient's head, 1 meter from her eyes, and she views the chart in a mirror 2 meters in front of her eyes. What is the distance from the patient's eyes to the image of the chart produced by the mirror?
Between A and B.
I need one answer. This is multiple choice, not multiple answer. Don't guess, reason it out. Which one of those properties of plane mirrors are you actually using to answer this?
B.
Okay. Why you say B? What's your reasoning?
The optician is too hold on. It's 2 meters away from the mirror, so it will be 2 meters behind the mirror, I guess. So when you add that up, that give you 4.
What are they asking us? They're asking us the distance from the patient's eyes to the image of the chart. So first of
Wouldn't
all,
it be
where is
two
the
two
image of the
meters?
chart?
Yeah.
Let's take this step by step. The chart is our object. So like my cup that was behind my head, and this is our mirror. Where is the image of the chart?
In the in the mirror.
Is it in the mirror? This is a plane mirror. Where is the image in a plane mirror?
The mirror?
Say it again.
It's reflecting to the mirror.
Okay, let's go back.
Behind the mirror.
Okay, there we are. It's behind the mirror. How far behind the mirror? So this is my image of the chart. What's this distance? All right, what is the object distance in front of the mirror?
2.
2. This is the object, and this is the mirror. What is this distance? Very good. 3 meters. So the object is 3 meters in front of the mirror. So how far is the image behind the mirror?
The answer is D.
Answer. I want you to answer these questions before we talk about the final answer. So tell me, what is the... All right, so if the object distance in front of the mirror is equal to the image distance behind the mirror, and the object distance is 3 meters in front of the mirror, what is the image distance behind the mirror?
3.
3, exactly. It's the same, okay? Object distance equals image distance for plane mirrors. All right? So the image is 3 meters behind, the object is 3 meters in front. So what is the distance now from the image to the patient's eyes?
6.
So here I am. I'm at the image right now, okay? I'm going to go 3 meters from the image to the mirror, okay? And then I'm going to jump again to get to the patient's eyes. How far did I move?
Oh, 5.
Right. 3 plus 2. So this distance from the patient's eyes to the image of the chart is 5 meters. So the answer is C. Okay? No guessing. All right? You understand how we arrived at that conclusion?
Yes,
Get it
ma'am.
now? Good, good. All right. I need you to go get a piece of paper and a pencil. Quickly. Any piece of paper, scrap paper. Got a piece of paper? Let me know when you got it.
Yes, ma'am.
All right. Do you see this picture right here? I want you to draw that on your piece of paper exactly as it looks on the screen. So take your piece of paper, make sure you draw it exactly as it looks on the screen. Your number 9. All right, done?
Wow.
Okay, now go find a mirror and hold that piece of paper up to the mirror exactly as it is. In the picture, the mirror straight up and your paper like this. And then tell me, draw on the other side of the paper what the image looks like. So draw like right next to it what the image of the number 9 looks like in the mirror. And then you're going to tell me which one of these pictures, A, B, C, or D, represents the image in the mirror. 1 minute. Go ahead.
D.
Somebody's already close to the mirror.
The answer is D.
So let others confirm. All right, so that was Ariana talking to me, said D. Carisha and Rose, did you get the same thing? Good, good. So you're absolutely correct. Okay. So why does it look like that? Well, when we hold up things like text, like writing letters, it shows it's easier to see one of the properties of plane mirrors that we call lateral inversion. Okay. And that simply means that we have a left, right, or a horizontal reversal of images in the object, in the mirror. All right. So that happens for the same reason why we were able to figure out how far the image of the chart was from the patient's head. Okay, it has to do with the object distance being equal to the image distance. If you remember in math, when you do graphs and you have to do translation, you have an object and then you draw a line and you have to draw the mirror image on the other side. You have to line up the points exactly as far from the original object on one side, and you have to go over that many blocks on the other side to get the mirror image. So if I did that here, if I took this point and translated it over here, then I would get another point right about here. If I took this point, did the same thing, translated it over, get another point right about here. And then if I took the bottom, yeah, my pencil. All right, took this point here, translated that, it would end up right about there. And then I would see the image in D begin to form. Let's see if I can draw. Okay. See? And that matches what we see in the mirror. Okay. So all our points have to line up. All right. Why is the word ambulance flipped horizontally? Have you ever seen an ambulance when it's parked? Did you notice that the words are backwards? Next time you see an ambulance parked, take a closer notice. So you might have never realized it because when you see an ambulance, you're usually seeing it from your rearview mirror. They're speeding up behind you, trying to tell you to get out of the way because they got to go somewhere. So the reason why the word ambulance is written like this is because of the property that you just observed with writing the letter 9 and looking at it in the mirror. It's because the plane mirror in your rear view mirror, the one in the middle, that you might take some time and turn it so you can look at your makeup, okay? That mirror inverts images laterally. So when you look in your rear view mirror, you're going to see the words look normal. And that's because by printing the words backwards, the lateral inversion has already been compensated for. So when the mirror now flips it flips it to the right orientation for us to be able to read the words clearly. But if you were to not look in the mirror and you just turn back and you look, you would see the words written backwards. Okay? So it's the mirror that inverts the object, inverts the image. Okay? So to make up for that, we just go one step ahead and we invert it ourselves. So when the mirror flips it, it flips it the way that we want it. All right. So on the front of an ambulance, the word is often written backwards in large letters. So why is it written that way? Is it A, to make it show up more clearly? Is it B, to make other drivers think about what it says? Is it C, so that it reads correctly when the ambulance is reversing? Or is it D, so that it reads correctly when seen in a car's rearview mirror?
D.
Exactly. Okay. D, so that it reads correctly when seen in a car's rearview mirror. So, to sum up all of those characteristics of plane mirrors, you can use this little acronym. Okay? Proper lane is very uptight, so don't start shouting. Proper, P for plane, lane is for laterally inverted, very for virtual, uptight for upright, so don't, same distance behind the mirror, and start shouting, same size. Okay? So very important to remember them all. Okay? And this PowerPoint is going to be made available to you. All right? So you can go over these throughout the week. And the last thing we need to talk about is this handy little device called a periscope. Okay? So a periscope is a device that's made up of a set of parallel lenses, mirrors, or prisms that allows an observer to view objects around obstacles. So we can see our observer here in the corner. He is standing behind a very high wall, but he's able to see a tree over on the other side of the wall by using this device. So what he's done is actually make use of the reflective properties of these plane mirrors, okay? By manipulating the angle of incidence, we can turn the light rays and change their direction so that they are focused around a big obstacle like this. So the light rays that come from the tree, they hit the first mirror and they make an angle of incidence with the normal. So what I'm drawing in purple is the normal for this mirror. Remember, the normal is always 90 degrees to the surface. So even if the surface is slanted, the normal is still 90 degrees. So if you're ever not sure about where your normal goes, you can kind of just, let's say this is the edge of my mirror and it's slanted. You can take your finger and you turn it into an L. So you now have a 90-degree angle, and you line up your thumb with the surface, and the way your finger is pointing is going to be where your normal will be. Okay? So if the paper is flat, it's quite easy to see that the normal just goes straight up. But if the surface is slanted, then you need to line up your thumb and your finger will tell you which way you should draw your normal. Okay? So when we draw in our normal, we see that our angle of incidence right here is going to be 45 degrees, and so is our angle of reflection. Okay? So blue arrow is my incident ray. Green arrow is my reflected ray. So all in all, the light ray turned 45 degrees twice, which gives me a rotation of 90 degrees. So it went from completely horizontal to completely vertical. Continuing to travel down now, this reflected ray now becomes our new incident ray as it's approaching the second mirror. So now it's completely vertical and it's going to strike the second mirror again at 45 degrees. So the same process is going to repeat itself. So we're now going to have the reverse happen. It's going to go from completely vertical to completely horizontal. This line here in purple is my normal. So in goes my incident ray at 45 degrees. And then it's reflected again at 45 degrees. And so we get another 90-degree, full 90-degree turn. And so the light is able to reach the observer without him having to move from his spot at all. Okay? And the reason we can do this is because light always travels in straight lines. So we can change that direction by simply lining up our mirrors at the same angle. Okay? So where is this used in real life? So if you think about submarines, they travel under the surface of the water. And so when the pilot or the captain, say the captain wants to see over the sea, he uses a periscope and he's able to see above the surface of the water by just simply turning it around to whichever direction he wants to see, and it works exactly the same way. Okay, that's a lot safer than trying to get out of the submarine and peep over the surface of the water. That's not going to work. All right, so one use of periscopes are in submarines to see above the surface of the water. Okay. All right, with that said, okay, yeah, sorry, that's how this is supposed to be, not the other way around.
Oh, so the light have to go
Yeah,
into the eye.
yeah, we have to be striking the 45-degree surface in order for us to get that effect. Okay, we can't be striking the plane surface. Sorry about that. Okay,
Okay, thank you.
let me draw my normal in properly. So this is my normal in aqua. Okay. That's my normal. So if you look, my normals line up. This is what I should have. In, down, out. Okay. We don't get that with the rest. This one would be like that. That's not right. This one, again, that's not right. And this one, again, that's not right. Make sense?
Yes, ma'am, in a way.
Okay. All right, so like I said, it might be easier to, like, if you don't know where the light is coming from, to go from the eye and go backwards. Because we know that this part right here, where it's coming from the eye, has to be pointing towards the eye. So we can work backwards and go up and then see if our answers make sense, see if we get those 45-degree angles. Okay, so if you don't know where the light is coming from, go backwards and start from the arrow that goes to the eye. Okay? All right. Yep. That's our time. So your assignment for the week, you're gonna have plenty of time now. Nobody's going anywhere. This is gonna be due on Friday though. So you have the whole week. This is the assignment. I'm gonna send it separately on Edmodo, but you can make it out pretty well from this PowerPoint right now. So you're gonna answer these questions. You can do it either on paper and send a picture of it,